Welcome back to our session. We're still talking about the acid-base theories. So the two theories that we are now familiar with is the Bronsted-Lowry theory as well as the Arrhenius. Now, in as far as the Bronsted-Lowry, an acid is a proton donor, while a base is a proton acceptor. And when we talk of protons, we talk about, the hydrogen ion, but which does not exist in isolation. So we'll think of it in terms of the Arrhenius theory that says to us that an acid is that substance that produces hydronium ions in solution, while a base actually produces the hydroxide ion. So now we shall look at acid-base reaction and try to look into the, the bolts and nuts in terms of how these reactions actually take place, in nature, right? So now we're looking at the types of reactions, okay? Now we are aware that acids, they ionize while bases dissociates, okay? So in as far as the acid-base reaction, we are saying that all acid-base reaction involve the transfer of the proton, okay? It can be multiple protons per unit, right? So when we talk about the proton, we're talking about the hydrogen ion, right? So the transfer of protons is reversible. So it means a substance can act as a proton donor, while in the reverse of that reaction, that another substance, accepts a proton to give us, an acid. So this is what we want to try and explore at the moment, right? So we are going to talk about conjugate acid-base pairs, right? Because we're saying that these reactions are reversible. Now, if we think of hydrochloric acid or HCl, in gaseous form as a proton donor, right? Okay, according to the theory, it is a proton donor. So that's a very straightforward definition of a Bronsted-Lowry acid. So now if HCl donates a proton to a water molecule, now what's going to happen? The water molecule is actually the proton acceptor, right? It's the proton acceptor. So if a substance is a proton acceptor, it means it is a Bronsted-Lowry base, right? So in this case, water is a proton acceptor, while HCl is a proton donor. So the transfer of the proton is from the HCl to the water molecule to give us that hydronium ion and the Cl minus. So this is the forward reaction, okay? Now, HCl is our acid, while water in this case is a base, right? Okay. Furthermore, we are saying that if we consider the very same reverse reaction, now, if HCl is an acid because it is a proton donor, when it loses that proton, it forms what is called a conjugate base, right? So this acid, when it loses a proton, it forms a conjugate base, right? Now, if we consider the reverse, take note of the arrow, the direction of the arrow. So we are interpreting this equation from our right to our left. What is happening here? This conjugate base actually accepts a proton from the hydronium ion. So this hydronium ion is a proton donor in the reverse reaction, okay? So if it is a proton donor, it means it is an acid, right? Okay, so what happens is the Cl minus is a proton acceptor. That's why we would call it a base. So this is a proton acceptor. So the transfer of, electrons, the proton is from the hydronium ion to the chloride ion. So in the reverse reaction, the hydronium ion serves the role of a proton donor, right? Okay. Now, in the forward reaction, this is what is happening. Let's look at the base now, okay? Water is the base because it is a proton acceptor. So if it accepts a proton, it forms a conjugate acid. This conjugate acid is actually the hydronium ion. It's an acid in the reverse reaction, as we have seen in the previous slide. So this is basically what is happening here, all right? Okay, so if we talk of a conjugate acid-base pair, now, the acid is HCl, okay? Then the conjugate base is Cl. So the pairs is HCl gas and Cl minus, okay? So this is the acid, okay? That's our acid, and that is our conjugate base, okay? So this is our acid conjugate base pair, right? And then also at the same time, we can say water is our base, and in this case, you know, the hydronium ion, H3O plus aqueous, is actually our conjugate acid. So this is the first pair, and this is our second pair. So this is what basically it's all about, okay? Right, so also in the reverse, we can talk about the chloride ion as a proton acceptor, while the hydronium ion is actually our proton donor, right? Okay, so in a conjugate acid-base pair, the substances differ from each other by hydrogen ion or a proton. Okay, so the difference is always the H plus. So if we can go back a little bit to those pairs, okay, if you check the difference between HCl and Cl is the H, okay? Also, if you can check the difference between the water molecule and the hydronium ion is actually 1 proton. So that's what this bullet serves to say to us, right? Okay, and then another case of a conjugate acid-base pair that we can talk of in this reaction, what is happening here, ammonia serves the role of the base, and in this case, water is the acid, right? Why are we saying water molecules, they act as acid? Because they are proton donors. So this forms that after donating a proton. So this is a pair. The difference between the water molecule and the hydroxide ion is the H plus. So indeed, this is a conjugate acid-base pair, right? So this is an acid, and then this serves the role of a conjugate base, right? And indeed, the difference is a proton, which is a hydrogen, you know, atom, right? And then also, if you look at the ammonium ion, it serves the role, according to the Bronsted-Lowry, you know, theory of acids and bases. The ammonium ion is actually our base, right? So if it accepts a proton, what happens? It forms the ammonium ion, right? So the ammonium ion in the reverse reaction becomes our conjugate acid. So this is our conjugate acid. Okay. And also the difference is just that hydrogen atom, right? Okay, so the proticity of an acid, it has to do with the number of protons a molecule or a unit of an acid can actually donate, right? It is an acid can donate 1 proton. It's called a monoprotic acid. So if we go back to this example of HCl, you'd realize that for every HCl, there is also just 1 that is donated. In other words, what we are saying is that according to this, an acid that donates 1 proton is called monoprotic. So the word mono means 1, right? Take note of that. Mono means 1. And then again, correspondingly, if an acid is diprotic, it means it produces 2 protons, okay? And then we also have got what are called, you know, polyprotic acid. So in terms of proticity of an acid, it has to do exactly with the number of protons that an acid can donate, but also it's still based on the theory of Bronsted and Lowry to say an acid is a proton donor, right? Okay, so an acid that donates 3 is triprotic. So anything that's more than 1 is actually polyprotic, right? Okay, just take note of that. Right, so that's as far as, you know, the proticity of an acid and also some of the reactions in terms of the conjugate acid-base pairs. So we need to do as much practice on this as we possibly can so that we become comfortable. For now, we'll go for a short break, and then after the break, we'll discuss more. Let's take a short break.